So we've made it through glycolysis. I know this looks super simple, right? We just had like 10 crazy steps of glycolysis. But endpoint of glycolysis is pyruvate. Now, what happens to pyruvate is generally determined by this system, this question of are you in an anaerobic or an aerobic state? Okay, so we're going to sort of take this high level view and talk about what happens with pyruvate. And one of the things to highlight here is in all of these processes, the purpose of what happens with pyruvate is to regenerate NAD+. So this is key. So regenerating NAD+ is essential to continue catabolic processes. So we're going to highlight how that happens, and it's going to happen regardless of whether there's oxygen available or not, but whether there's oxygen available or not is ultimately going to determine what happens. So before we look at this picture here, I want to kind of put something down on paper that we sort of talked about last semester as a way to think about the fates of pyruvate. So again, if we've got pyruvate here, if we are under anaerobic conditions, okay, so there is not oxygen readily available, okay, we are going to be undergoing fermentation processes. And I'm using this word we a lot, but there's actually two fermentation processes that are highlighted here. Homolactic, that is the we do homolactic fermentation, and then alcoholic fermentation. So we'll talk about and differentiate how these both do sort of the same process, but do so through different mechanisms. And again, alcoholic fermentation is not something that we are able to do. Now, something else we are able to do is what happens under aerobic conditions. So under aerobic conditions, there is oxygen available. And in that case, we go through pyruvate dehydrogenase chemistry, and we're going to generate acetyl-CoA. Right, so that's acetyl-CoA. We snip off a carbon as carbon dioxide. So again, that's pyruvate dehydrogenase chemistry. Okay, and then the citric acid cycle is going to take over. So the citric acid cycle is going to take over. We're going to fully oxidize all of those fuels to carbon dioxide and water. And importantly, in this process, we do regenerate NAD+. So we're going to kind of highlight that. But that's sort of what we learned about last semester. So what we're going to do right now is just sort of highlight and map on where these are on this picture here. So before we kind of delve into the picture, we're going to see lots of images like this. One of the things I love about these images is there's so much detail sort of embedded in the details of this. One thing I want to fix here is one of the things that you can look at is see whether arrows are one-way arrows or two-way arrows, and that tells you whether or not a process is reversible. So I don't like that it indicated that glycolysis was not reversible there, because glycolysis absolutely is reversible, and the reverse of glycolysis is gluconeogenesis. Okay, so I wanted to fix that, but highlighting here, look at these other systems here. This is irreversible. Okay, this is another irreversible process here. Okay, so we're going to highlight and name sort of what these are, but just the details in those arrows are really important to what's going on. Okay, so let's start over here, just like we talked about fermentation processes first. Let's talk over here on the left with sort of the different fermentative processes that are available, again, for pyruvate. So noting that both of these serve to regenerate NAD+. So that is key here. That's why they happen. So let's talk about, again, very generally, we're going to have a couple of slides here that talk more about the details of this. What is homolactic fermentation? Well, homolactic fermentation basically takes pyruvate and converts it to lactate. Pyruvate to lactate is a reduction of that molecule. Okay, so we must have a subsequent oxidation of something else. So what is oxidized is NADH to NAD+. Again, purpose is we regenerate that NAD+. Now, importantly, this is a reversible process, so we'll talk about, well, what do you do with lactate now? That was sort of a short-term fix to regenerate NAD+, but now what do you do with that lactate that's generated? So we'll get to that in another video here. But what bacteria, yeast, anybody who does any brewing. This is the biochemistry that happens to allow those systems to continue to operate and generate energy in an anaerobic sort of system. And that's where pyruvate undergoes in a two-step process: generation of ethanol, that's what makes your beverage alcoholic, and then CO2, that's what makes your beverage fizzy. Okay, but want to make sure to highlight here that this process is not us. Okay, so, but the intent is that we undergo these anaerobic fermentative processes to regenerate NAD+, and that's important because this NAD+ is required to continue glycolysis. Okay? So moving over to the left side here, this is what happens under aerobic conditions, right? We can see the details that we talked about kind of down below, where you're going to have, and they actually show this sort of in kind of lumped together, which I don't necessarily love. We've got pyruvate dehydrogenase chemistry that generates the precursor that can then go through the citric acid cycle. So we've got the citric acid cycle here. The citric acid cycle actually generates more NADH. So we still haven't yet regenerated that NAD+. What we really have to regenerate that NAD+ is electron transport and oxidative phosphorylation. It's really the electron transport piece that's responsible for regenerating that NAD+. Because remember, the electron transport chain, we're going to take the electrons that are held in NADH, they give their electrons to the electron transport chain, and that is how and when we regenerate NAD+. Okay, so lots of things to think about with what happens with pyruvate. Glycolysis, again, being an anaerobic process that occurs in the cytosol. Once we start needing to do aerobic processes and we need to dip into the mitochondrion, and that's kind of what's shown over on the left here with red, we really need to think about what options are available for us.